In this video, we will introduce the squeeze theorem. Now, the squeeze theorem is going to be a property that allows us to conveniently evaluate certain types of limits. So let me go through the statement of the squeeze theorem and illustrate it graphically before we apply it to an example. So if we have three functions f, g, and h, where f of x is always less than or equal to g of x is always less than or equal to h of x, near some value c, where c is maybe where we want to take the limit of g of x. And what the squeeze theorem tells us is if the lower function and the upper function both have the same limit, then the thing squeezed or sandwiched between them will have no other choice except to have that limit as well. And I think this becomes much more clear from the graphical perspective. So in the example that we have illustrated graphically, it appears that at x equals 1, it looks like the value of the limit is 1 for all three of these functions. But what we see is that we have f of x is less than or equal to g of x is less than or equal to h of x. And because the limit of the lower function is 1, and the limit of the upper function, the h of x, is 1. That is, when you plug in inputs close to 1, the lower function has outputs really close to 1, and the same thing with the upper function. That means that if this red function g, which is squeezed in between, as you approach 1, there's no other way for it to do anything but have values close to 1. So then, by the squeeze theorem, and we'll oftentimes shorthand notation that, abbreviated as ST, so by the squeeze theorem, the limit of that function in the middle also is going to be 1. And I think the picture really gives that just great intuition in terms of what the actual statement is claiming. So let's look at a very typical example. Use a squeeze theorem to evaluate the following limit. Now, the difficulty arises in the fact that I've only given you one function, and if you go back to that statement of the squeeze theorem, it involved three functions. You need the lower and the upper function as well. And you need both the lower and the upper function, in this case, to have the same limit as x approaches 0. Now, dealing with a function like sine is extremely convenient. When we discussed the basic properties of trig functions, we noted that the value of sine, regardless of the input, is always bigger than -1 and always less than or equal to 1. And we would like to build this up so that the function in the middle is x squared sine 1 over x. So what we need to do is take the x squared and multiply the inequality by it. And since x squared is bigger than 0 when x is not 0, we will not change around the direction of the inequalities. So minus x squared less than or equal to x squared times sine 1 over x is less than or equal to positive x squared. And now we are in an ideal situation to apply the squeeze theorem. So since the limit as x approaches 0 of minus x squared, that is a polynomial function, we can use the substitution property to evaluate the limit and get back 0. And the limit as x approaches 0 of x squared is also the limit of a polynomial function. We use the substitution property, we get back the limit is 0. So since these two limits are 0, it follows by the squeeze theorem that the limit of the function in the middle is also 0. So that would be the limit as x approaches 0 of x squared sine 1 over x is equal to 0. And when applying the squeeze theorem, a couple key ingredients to keep in mind is if you are building up to the upper and the lower function, you do need to demonstrate, at least write down what their limits will be. And if their limits are both the same, you should indicate what property is giving the desired conclusion. by the squeeze theorem, we get the following value for the limit.